stuff, let's have a look at our next problem. So this is going to be a problem using a two-sample z-test for proportions, and what this test is all about remembering is that we have a risk difference. So this is basically a test on a risk difference, so we need two binary categorical variables. So let's have a look at the problem. It's the same problem as my video where I looked at the risk difference, relative risk, and odds ratios. So have a look at that problem. It's going to be the exact same problem that we're going to state. So researchers randomly select 242 subjects from a population of people in a care facility. So once again, that's a cross-sectional study design. And so both, whether you're a veteran or not non-veteran, that's random. And whether you have sleep disorder or not sleep disorder, that's also random. So a random proportion of the subjects are veterans, and a random number of the subjects suffer from sleep disorders. So the researchers want to test the claim that the risk of sleep disorders is different in veterans compared to non-veterans. So again, a total of 77 veterans had a sleep disorder and 45 did not, and a total of 35 non-veterans had a sleep disorder and 85 did not. Those are my four joint frequencies. Use a two-sample z-test for proportions to determine if there's a difference in the risk of sleep disorders comparing veterans to non-veterans. And so let's have a look at this. Once again, there we have the summary of our results. So we're going to start with step one. So when you start with step one, and step one, remember, that is just stating what are the population's parameters of interest. And the population parameters of interest, really, that is the probability of disease given exposure and probability of disease given not exposure. And please write out in words, that's the probability of a sleep disorder in veterans and a probability of a sleep disorder in those that are not veterans. Those are these two parameters. We can also call them P sub 1 and P sub 2. And then in step number 2, we look at what would be the null and alternative hypothesis. Well, the null hypothesis is that these two, P sub 1 minus P sub 2 equals 0. The risk difference, remember, that minus that is the risk difference. So the risk difference is 0. And the alternative hypothesis, well, the risk difference is not equal to 0. Now, I don't put those hats on. Remember when we put the hats on, which you should strictly do when you talk about sample data, but this is population parameters. And so we don't put those little hats on, indicating the fact that these are population values. And so step number 3, I think we were told in the problem to use, unless otherwise stated, but we are told to use an alpha value of 5%. Step number 4, what test are we going to use? Well, it's the two-sample z-test for proportions. And so let's have a look at the assumptions for the use of this test. I'm not going to write them out, but we need the samples to be independent of each other, and we can assume that is so, that these samples are randomly selected. We can assume that is so, and then we need the sample sizes to be sufficiently large so that the sampling distributions of the sample proportions is approximately normal. So what we want then is for these numbers to be, if we look at these proportions, for those two numbers to be at least 5. So we talk about the frequency of the veterans with sleep disorder in veterans and the sleep disorder in non-veterans. We really need those numbers to be at least 5, and we definitely do have that. And if that is also, which we do have, where's my green pen, we're going to have that this difference between these, or at least this difference between these two, are normally distributed. So we're going to say that this P sub 1 minus P sub 2, we're going to say that that is normally distributed. It's a standard normal distribution under the null hypothesis. So in step number 5, let's have a look at this test, the statistic that we need. So we're going to say step number 5. Step number 5, let's do that. We have that Z is equal to P sub 1 minus P sub 2, but we put little hat symbols on top because, remember, these are the population values, but we are getting this from sample data, divided by some standard error. Now the standard error we have to talk about. So the standard error is going to be the square root of P hat. Now we still have to say what P hat is. That's the pooled proportion. And so we're going to have that times 1 minus P hat and we're going to multiply that by 1 over n sub 1 plus 1 over n sub 2. And n sub 1 and n sub 2, that's actually n sub 1 plus n sub 2 plus. Remember, that is just the frequency of veterans and the frequency of non-veterans. And remember, that is normally distributed 0 and 1 under the null hypothesis. So let's calculate this z value of ours. Well, first of all, let's just have a quick squiz. We haven't done that yet. How do we calculate this pooled proportion, pooled sample proportion? Well, that's actually very simple. If we go back, let's mark these as n sub 1 1, n sub 1 1, n sub 2 1, n sub 1 2, n sub 2 2. That is a very easy calculation, this pooled. In the end, have I got the right pen? Yes, I do. In the end, we're going to have n sub 1 1 plus n sub 2 1. So that is actually n sub plus 1. In other words, everyone who has a sleep disorder, and we're going to divide that by how many people we have in our study. So that's a very easy calculation. So we really want for this that's the wrong color. Let's not go for that. 112 divided by, we have 242. Okay, so how many people had the sleep disorder? 112 divided by 242. That's going to be p hat, and you have to plug in p hat there, and again, n sub 1, that's 122. N sub 2, that's 120. So this is really just recognizing what you should plug in where. And so if I calculate a z statistic, let's write this all out, because I think it might get slightly confusing. So let's have a look here just at what p hat sub 1 is. Remember, that's our probability of disease given exposure. So that is the probability of exposure. There's 122 people were exposed. Who got the disease? 77 over 122. So that's 77 over 122. And p sub 2 hat, those 35 had a sleep disorder that were not veterans. So that's 35 divided by 120. So that's what you're going to plug in for p hat sub 1, p hat sub 2. This is what you're going to plug in for, the very easy, for p hat. And again, n sub 1, that's going to be 122. N sub 2 is going to be 120, the frequency of exposed and non-exposed people. So if you plug that in for your z value, I get a value of 5.29. So, pause the video, plug in those values, see if you can get a value of 5.29. And we recognize that as a very large number. So definitely we're going to reject the null hypothesis. And if we do that for step number 6, the z critical value, remember that would be on the following, that's alpha. So we want alpha to be alpha over 2, we should say, because we want, if we look at our standard normal distribution, we want the 2.5% of the area under the curve and 2.5% area under the curve, and that's on the standard normal distribution, so that of course is going to be 1.96. And we have that our z value that we have is larger than 1.96. So we reject the null hypothesis and we accept the alternative hypothesis. Okay, so what we're doing here with this test is it's not a test that we often use, but we're looking at this risk difference. Is this risk difference 0? Under the null hypothesis at 0, we can express this risk difference per units of standard error. And there in the denominator is how we calculate the standard error of this risk difference. And it turns out that ours is quite big, our z value 5.29, and we reject the null hypothesis. So all we have to do is write a test conclusion. So I've written there's enough evidence in the data at the 5% level of significance to show that the risk of a sleep disorder is different in veterans and non-veterans. In fact, because I have to reject now, I have to say what our findings are. In fact, the risk of a sleep disorder is 33.9 percentage points higher, I could say, in veterans compared to non-veterans. Where do I get that? So let's just put that out there. Remember that p hat sub 1 minus p hat sub 2. Remember that's the probability of disease given exposure minus probability of disease without the exposure. That's the risk difference. For us, that was 0.631, if you calculated that, minus 0.292, and that was going to be about 0.339. That's positive. That's a 33.9 percentage point increase in the risk of a sleep disorder for veterans compared to non-veterans. So let's have a look at what ChatGPT does. As you can see, I'm using ChatGPT 03 Mini High. I have copy and pasted my problem. Do remember, for these problems in ChatGPT, I use LaTeX notation for all my mathematical typesetting. In this instance, they're only numbers, but there I want the mathematical typesetting of the test statistic Z, so I do put it in dollar symbols. Let me know in the comments down below if you want to learn a little bit more about LaTeX or LaTeX. Mathematical typesetting, it allows you to put equations into something like ChatGPT. So there's our problem, just as we've stated in the written part, but I am instructing the LLM to generate a solution to this problem using the following 7 steps, and I do outline the 7 steps that we use. So it's very correctly stated. There's our 2 population parameters, P1 and P2, the true proportion of veterans in care facilities who have sleep disorder, and the true proportion of non-veterans in care facilities who have sleep disorder. So probability of disease given exposure, probability of disease given not exposure. And our null hypothesis would then be, it does write it out in this form that P1 equals P2, but we do like to write that as P1 minus P2 equals 0, just to indicate that the risk difference is 0. And remember, this 2 sample Z test would be about the risk difference. And then alternative hypothesis that it's not 0. Level of significance, 0.05, great. We're going to use the 2 sample Z test for proportions. It's stating the assumptions there that all these observations, at least, are all independent. Everyone is randomly selected, no problem. And then the sample sizes are sufficiently large so that the sampling distribution of the sample proportions is approximately normal. So we want our 2 frequencies to be at least 5, as we've discussed. Now we're going to calculate the test statistic. Now for that we need P sub 1 hat. That's the estimate of the probability of disease given exposure. We've calculated this before. It's 0.631. And for probability of disease given not exposure, it's 0.292. And then we just simply need the P hat, the pooled proportion. And as you can see there, the 112 divided by the 242, just as we did, that gives us this pooled proportion. And when we calculate the standard error, that's going to be that pooled proportion times 1 minus that pooled proportion, and 1 over n sub 1 plus 1 over n sub 2, where n sub 1 and n sub 2, remember, there's my 122 and my 120, just as we had. You plug in all of that, you get a Z value, P sub 1 hat minus P sub 2 hat, the risk difference, divided by its standard error. You get a value of 5.29, just as we had. Now that is normally distributed with a standard normal distribution. So our decision rule would be, or a critical value is going to be 1.96. And indeed 5.29 is much larger than 1.96. So we reject the null hypothesis and we can write the conclusion there as we think, as we saw in the pen and paper. So as we've seen. Now I went one step further and I say, thank you. Could you also create a plot of the standard normal distribution showing the regions of rejection for 5% level of significance and show the value of the test statistic? And it gives me this Python code, and I've done the following. So I've pasted this into a notebook. So if you go to your Google Drive, you say File New, and instead of Google Sheets or a Google Doc, you'll say a Google Colab notebook. And you can just paste this code into a Google Notebook, and there's the result. And you can clearly see here very nicely, there's our standard normal distribution centered at 0. We can see our regions of rejection at 1.96 and negative 1.96. So of all possible Z values that we could get under the null hypothesis, these would be the 2.5% least probable in the lower tail, 2.5% least probable in the higher tail. And if we look at our test statistic of 5.29, that's well within the region of rejection. And hence, that's a very improbable Z value to get under the null hypothesis, and we reject the null hypothesis.